For the next talk, we are happy to welcome Dobromir Dotov. Dobromir, or Dobry, is a postdoctoral fellow at the Large Interactive Virtual Environment Live Lab at the McMaster University, Ontario. He has worked on motor learning, gait in Parkinson's disease, and the interconnection between auditory and motor systems in human and macaque. Today, Dobromir is going to present a model that supports the findings of his research that show that performance stability of human musical group increases as group size increases, similar to the collective dynamics of swarming and flocking animals. Dobromir, thank you for joining us today. Take it away.
Thank you. Thank you for the introduction, and thank you for organizing it, for that you have managed to keep this running. I know with the pandemic, things got really strange and complicated. Okay, so let's head to the problem that motivates my research. If I can actually control my slides. Yeah, so when you get a lot of people together, we say that kind of the way we can describe this is that crowds sometimes can feel and act like one. Whether it's in political protest or religious ceremony or something else, when you get people, and especially if you have some kind of a ritual movement or ritual sound, chanting, for example, things can acquire at the collective level a very special kind of intimate feeling, which I'm not going to describe. That's not my project, it's not my job. I'm going to instead talk about something else, which is more about how they synchronize. But before I get there, let me give you one more example. Just the power of collective synchronization. Okay, so this is, I don't know if we can count this, but there's lots of people chanting exactly the same thing together, and they feel really strong at this moment. And there's another version of that, which is not so, the experience is not maybe necessarily so deep, but it's also relevant. These are football or soccer fans that before the game, they're starting to warm up and cheer for their team. In this case, they were actually shouting profanity, so I had to mute this part. Okay, so I want to understand how large groups of people come together and coordinate. And I would like to start figuring out what principles are involved. So that will be my approach. I'll try to find or borrow some principles to help me explain what's happening. And as maybe you have been reading, depending on your research more or less, there's a lot of work in very interesting literature on dyadic interaction. Oftentimes the tasks involve synchronization, repetitive movements, and from that you can find one way of addressing what's happening is by assuming some kind of a mutual predictive mechanism. So it's easy to go this way. You have two brains and two bodies interacting with each other, and you can start imagining all sorts of theories about how the two brains are predicting each other. But I'm curious, if we start increasing the group sizes, is this theory going to work well? Now, I suspect that it's not straightforward, just because before I even take you to the studies and to the other theories, just imagine if you extrapolate this theory to a larger group. So what does this mean? That in a group of 8, you have each participant is predicting all the others, and maybe there's like a second order prediction, and you're predicting what they're predicting about the others. It becomes kind of crazy. So maybe this approach is not the ideal. So I will try to show you with the study and with the model after that instead of just projecting some ideas and theories that we have, the field has developed for the dyads, we can maybe even go the other way. We can just go from the collective down to the direct one-to-one interaction. Okay, so my task is a group drumming task. At first, we started with just buckets, and it was a bucket drumming task. They were they were instrumented so we could record the onset time. That's when the participants hit the drums. But then we switched to something a little bit more high tech. So these Yamaha digital drums record the onset times, and participants hear their own drums through the speakers in front of them. So this is a snapshot of the one sample trial, one sample session. In the center, you see a big speaker. This speaker delivers the stimulus. This is important because for the task which I'm going to show you right now, the stimulus is what starts the trial. So it's a synchronization continuation task in group. This task has been used a lot to study timing in individuals, and then more recently timing in dyads. I'm going to just study even larger groups. The basic data that we work with are the onset times. At the beginning, the metronome will give some pattern that the participants have to reproduce. And for this part of the study, it's all very boring, very simple metronomic drumming. Excuse me. And then the participants have to, they're instructed to maintain this pattern, to maintain the tempo, which by the way is not easy, and to still stay synchronized with each other. So we have group sizes of 2, 4, and 8, which we call dyads, quartets, and octets. And to be able to compare and to compare to previous studies, but also to tell how the individuals' roles change when they play together, we also recorded solo versus ensemble, which means that for the participants who drummed together, the same ones were also taken in separate rooms, and then they performed the same task alone. Although I have to say this is only for the dyads and the quartets, because just logistically it's too hard to do this for the octets. If you have to run 8 participants individually and then wait, the other ones have to wait for them, it becomes too complicated. We have a range of tempos, which in this study turnout is not a huge factor, but you just, I guess the interesting thing we found out when it's too slow or too fast, the group just fails. So we didn't analyze the slow ones and the very fast ones. And using the onset times, which we recorded with by MIDI on the computer, we started to extract the dependent variables, the things that we measure to characterize how the individuals were doing the task. So the first level of variables, I call it the first order measures. This is the variability of the inter-onset times. So the intervals between the black lines, how variable they are for the individuals, how much the tempo changed, speeding up. And that's important because for the part of the field and the community that I interact with a lot, timing and auditory motor neuroscience, that's an interesting question to understand why individuals tend to speed up spontaneously. It's a very frequently observed phenomenon. When you ask individuals to tap, they tend to speed up. And when you put 2 of them together, they speed up even more. And then the autocorrelation of these intervals, which is one way of starting to understand the dynamics. Then at the second level of the variables that we can extract, we have things that describe how individuals coordinated with each other. So this is the cross correlation and the transfer entropy. So if you see in the lower right corner, you have these schematic illustrations of a duet, quartet, and an octet. In this particular case, the lines, the thickness of the lines indicates the weight, the magnitude of the transfer entropy. And then there's more, but probably there won't be time to talk about all the measures. So one more thing I need to add, which is important, is we added a theoretical thing to the analysis. So this was, we defined a group aggregate. The group aggregate was basically a point that falls somewhere in between the onset times of the individuals. When we pass a kernel, we convolve the events of the individuals, we get the point in the kind of in the center And this we define as the group onset time, which is important because we want to see how the group behaves. We want to see this interplay between what individuals do to support the group performance. At the end of the day, they're told that they're there to perform as a group, as an ensemble. Okay, let's start with the results. The first thing that we observe, and I need to tell you quickly what these bars are. On the left, the first bar is the variability of individuals drumming alone. The middle one is the variability of individuals drumming together. And the third bar is the variability of the group as a whole. So what you see here is that that's already one interesting finding. When individuals are put together and they try to synchronize with each other, their individual variability increases. So they sacrifice some of their own performance for the sake of achieving a lower variability of the group as a whole. That's kind of interesting. You can think about it, but before we get there, let's see how the other groups are doing. So for the quartets, we see the same pattern. And then for the even larger group, the octets, yet again, we see the same kind of pattern. And just as a reminder, we don't have a bar here because we didn't run the participants from the octet groups individually. So there's nobody here to make the bar. In addition to this interplay between individual and group variability, we also see something else that's interesting, is that as the group size increases, this effect is amplified. So the individuals on average get even more variable, and the group as a whole gets even more consistent. That's a kind of, you can go in the ideas and models of collective behavior. That's one thing, that one signature is in some systems that behave as a synergy. Now, let's go to the next variable. Speeding up, like I said, that's something that's interesting to some of us in the timing community, because we know, and it's still not that obvious how it's not that easy to explain. So what you see here is on the y-axis, that's just the slope of the tempo along the length of the trial. So a positive slope means that they're speeding up, so tempo increases. And as you can see here, individuals speed up when they're playing solo, but when they play together, they speed up even more. And that's actually something that we know. But what's more interesting is that this is not amplified for the larger groups. So this is when we get to some of the, when we get to this comparison between different theoretical approaches, because if you read some of the literature, they will tell you the more prediction, the more mutual prediction is accumulating together because you have more participants, the more they should be speeding up. So the prediction is that these bars, the bars that are higher, they should keep getting even higher for larger groups. Instead, we see the opposite. So somehow in this context, at least, the group size is stabilizing performance, but it's kind of going against some of the predictions of mutual prediction-based theories. Then something else that we can learn from analyzing, in this case, the cross correlations, borrowing from the existing literature, you can get this pattern of positive, negative, and then positive again, cross correlations, depending on the lag. So we're just focusing on lags from -1, 0, and 1. And you can interpret this. This particular pattern is interpreted as mutual prediction. And let me try to explain very quickly, because I don't know if all the viewers and listeners are familiar. What this basically means is that if I take your drumming intervals and my drumming intervals, they're kind of misaligned by 1. So for every short interval that you produce, I'll make a long one. And then because I made a long one, I'm late. Next time you compensate and you'll be waiting. So you produce a long interval, whereas I'll compensate in the other way, I'll produce a short one. So we end up in this pattern, short, long, short, long. And you see this as this positive and negative cross correlations with respect to lag from -1, 0 to 1. But the important thing to see, after having explained how the metric is interpreted, the important thing to see is that we lose the pattern for larger groups. So if you see it with different colors, 2, 4, and 8, in all the tempos, the pattern of this alternating compensation is lost. And individuals basically just somehow tap consistently, but they don't mutually predict or mutually compensate for each other. And also, this is not consistent with the idea, the pattern of results is not consistent with the idea that some particular participants take leadership role. If there are some who are taking a leadership role, then you see a different, more pronounced pattern in the red line, which is the octets. So that's a second way in which we are finding evidence that is not consistent with the basic dyadic mutual prediction theory that is out there. And in the interest of time, because time is going, I will skip the interpretation of the transfer entropies because it's not that actually easy to interpret anyway. But yeah, we just, I guess it's enough to mention that individuals have stronger coupling in some sense amongst each other, but the group as a whole becomes has less causal density according to this particular measure. Okay, so the important thing, one very important thing for me, I think is useful here, in addition to showing you these variables and these effects and interpreting them in light of existing literature, it's useful to understand them, is to model them. So I'll try to show you now a model, a dynamical system that reproduces at least some of the results. And then we can use that model and what's in it to make, to be able to say more about collective synchronization. So I borrow my intuitions from the animal literature, collective behavior in the animal world, with models. One of the very popular ones is the Kuramoto model of group synchronization. The very useful and important thing here is that it's a very, very fast crash course in the Kuramoto model. The reason why people are excited about it is this term here with the stuff that's inside the brackets. This is the phase between two periodically behaving processes, right? The difference between this phase between two individuals determines how much the phase of the individual will change. So this is the driving thing, is the difference between the two participants, but it reduces to just the mean field. So something, I'll call it the mean field, the average of all the individuals. So in this case, even mathematically, the individuals are coupled, or they can be expressed equivalently as being coupled to the mean, the group as a whole. So we'll use this model to give you now, instead of showing you, explaining the equations, I'll just show you some examples. This is a simulation with 8 oscillators that are coupled, and the degree to which they're pushing each other is represented by the thickness of the lines coupling them. So, okay, so there's nothing particularly exciting happening here. This is just 8 oscillators more or less synchronizing, but I can switch to the next view. So this is the same simulation, just shown in a different way. Instead, I'm showing you how they're coupled to this, let's call it the mean field, the average of the individual phases. So when they're, I can basically explain what's happening. I can make sense of what's happening by just assuming that they're coupled to the average. Okay, so now to unpack a little bit more this model. Psi has, being the average of phases, it has two, let's call them parameters. The direction which is pointing, which is the phase, which is how you see that the individuals are synchronized to it, but also the length of the line, the magnitude. And this changes as a function of how consistent the individuals are. I'm showing it here in a figure from a different simulation with more units, just to be clear. When the units are spread around randomly, then the length of the line is small. So we say that the magnitude of the field is very low. Whereas as they keep getting more and more clustered, so they get synchronized, the magnitude gets larger. And you need to remember this to understand how the model works. So what the model does is, as the individuals get more synchronized, the mean field has larger magnitude. As it has larger magnitude, it exercises a stronger effect and it pushes them more. So it's a positive feedback loop in a way. Let me show you again. Now watch how, as the black lines start to get synchronized, the blue line will grow in length, and then it will kind of force them, it will push them into a collectively synchronized state. Okay, so this is kind of the essence of the model and the essence of what I believe is happening, is important to understand in the case of group synchronization among humans, is that you can explain a lot just in terms of the mean field and how the individuals stop paying attention to each other. Instead, they're just behaving like a group that's coherent. Now let's say a few more things just to conclude. That's maybe not so important, but we had to modify the original Kuramoto model because it wouldn't reproduce all the results. So instead we gave it a discrete coupling. So individuals are not coupled throughout the whole cycle. They're just coupled when they produce events. So this function here, when 0 is when I drum, is just after that with a short latency. After that is when all the others in the group will hear me or will be coupled to me. And there's noise also. Okay, the model reproduces the data for the variability. So the individuals have higher variability than when they're coupled to each other. So when they're moving together versus in solo. And the ensemble as a whole has less variability. And as you can see, these effects are amplified by group size, so which is the same thing that we see in the behavioral graph. So, and with this, we can start the recap and go to the kind of the implications. So group drumming is stabilized by larger groups. It behaves like a collective phenomenon. We don't see so much evidence for mutual prediction, and it will be hard to make sense of mutual prediction n-way situation anyway. Instead, I make sense of this as a coupling with the group aggregate, which is created. This is the more important thing. The group aggregate is not a separate thing, it's created by the individuals. So it's not a separate piece in the model. No, there's no separate term in the model for that. We don't think it's a separate, there's a separate piece in the brain for that either. So by definition, the thing that's driving the whole synchronization is a collective entity. And with this, I think I should conclude. I have a few more things to say in terms of implications, but that's not necessary. So I think we'll stop here.